kind of loud. Looking at the quiz now to make sure that I had it on, but I had it muted so you won't be able to see the questions beforehand. To make sure you learn from the quiz, because the quiz grade is a pretty small part of your grade. The learning is the goal here. So number one, what does vacuum mean when used scientifically? So when used scientifically, you know it's going to get rid of cleaning machine, right? So which one of these is vacuum? No pressure. No pressure, right? Number two, why is the buoyant force of a potato, Amber, higher when it is submerged in water than when it is in air?
That was not my question.
It wasn't yours? I thought it was yours.
Mine was the vacuum question.
Oh, okay.
I wonder why you got it wrong.
That's yours?
No.
Oh. Okay, well, let's
I
not.
think it might have been hers.
Jessica's?
Yeah.
What do you say? What makes something float?
Pressure?
It's actually not pressure.
Really density. But I was thinking like the pressure of water. Because there's higher pressure in water than there is. She makes questions.
It's
I literally answered it and then I used it.
okay. So let's make sure we understand this, because it seems like there's a lot of people who had different views when they first took it.
I think you're pretty skinny. That's the
We-
whole thing. That's
Oh,
not even an
Well, I
option.
know, but
Yeah, that's what I was thinking. Something. Okay, buoyancy. What we learned from Archimedes from the lab is that the buoyant force is equal to the weight of the fluid displaced. So it has to do with the density of the fluid displaced and the volume of the fluid displaced, since density is mass per volume. The downward force on the object is its volume times its own density. So the buoyant force is the volume displaced times density of water. The downward force is the density of the object times its volume. If it floats, the volume will be larger than the volume displaced. If it floats, it doesn't displace water equal to its volume, otherwise it'd be submerged.
Yes, but also
Yeah.
the pressure in water is higher than air.
I'll address that. You're partially thinking right and then partially wrong. So in the end, if they had the same density, the buoyant force would be the same as the upward force, because it would displace water equal to its volume and it would weigh the same. If it's more dense, it's going to displace the same amount of fluid but weigh more and sink. If it's less dense, then if it were to displace the same amount of fluid, it would go upward. And so it floats out to the top where it doesn't displace as much. So the difference is the density. Lower density things always float on higher density things. Now, to address the pressure thing, the reason buoyancy works is because pressure increases as you go down in depth. It's not what the pressure is, it's the difference in pressure from the top to the bottom. And since the pressure is the result of the weight of the material above, then that has to do with density and gravity. So if you were in a no gravity situation, nothing would float.
And that's why I was thinking pressure, because it says when it's submerged. So when you push it down, I was thinking of the pressure.
But the key is you can take air and you can pressurize the air. And it's not going to make the potato float up. Right? So it's not the pressure, it's the density. Okay, hopefully that was a learning question. Going to the next one. If the temperature outside is 0 degrees Fahrenheit, 0 degrees Celsius, what is it in Fahrenheit? This was Lindsay's question. 32. And I do expect that's the kind of thing that you will have in the old memory banks. You do have the equation to convert when you're taking the test. So if you didn't know this on the test, you could do the calculation. But if I were to give this question on the test, it would be with an expectation that you actually just know 0 degrees Celsius is 32 Fahrenheit. Which is, what's special about that temperature? Freezing temperature for water. Finally, what is the definition of heat? It's now, I forgot who wrote this question. Hannah.
I know, I messed up on this.
Are you a Rick Castle fan?
No.
No. Okay. Because if you watch the TV show Castle, it had the fictional character Richard Castle, who was the novel writer. And then they hired somebody to write a bunch of Richard Castle novels, so the novels existed. And Nikki Heat was the main character in his novels. And the name of one of the novels was, there's heat rising. I think there's also temperature rising. So I thought maybe you were playing on that. Okay. So learning from this and hopefully also scoring well, right?
No. I got 2 out of 4. Because I thought 2 was C. Because I feel like we talked about that.
Remember, it's the difference in pressure that causes buoyancy, not the pressure itself, but the difference. So if water was completely incompressible, which is the way we treat it in a class like this, you could pressurize the water, or you could take a potato and put it down at the bottom of the ocean, and its buoyant force would be the same as at the top of the ocean, assuming the potato itself isn't compressible, which is a bad approximation. Oh, yeah, that's only one page. The rest of it's on this slide. Okay, so getting into the fun of it. Yeah.
Are we going to go over the homework at all?
Oh, we can. You got questions?
Yeah, I forgot my book though, so I don't remember exactly which questions, but I know it was like towards the end.
Okay, it'll take me a few minutes to pull it up, but I will. Union College, Lincoln, Nebraska, where the sling of the ink, push the pen along. So did we, perchance, win our last basketball game of the season last night?
No, we're close though.
Yeah. We did the other one. I'm just curious. Like, I'm not trying to
They won one game.
downgrade the team, but I swear there's no way.
They won one game, and that is what we'll have to take. I feel. You're on the team, are you, right? Actually, I can check right here. Bryce. It says Bryce Nelson instead of Bryson Nelson. And you're the only. Well, no, you and Benson are the only people who aren't 6 foot or 6'4", apparently.
Joel is over 6 foot tall.
It doesn't matter.
The minimum is 6 foot for coach. So.
Yeah, it just cracks me up. I've got Ryan and DJ in my class. Like, you're not the same height.
You can hang by your feet. No, I'm just kidding.
Okay, looking at the.
How tall are you?
Like 6'1".
So you're actually the height it says?
Yeah, so it's like 6 foot, but if you're above 6 foot, you can put it.
I just want to know how short I am.
We're not looking at homework 4, right?
Why he's doing this?
And it was like,
Look at this.
that's nice, Joel.
Yeah, you're like level
I could be his deodorant.
Staying on topic a little. Very sounds question. Which one?
It was,
So she would be a 6
11,
foot.
and I think maybe 15 was one of them too. I don't remember how trouble with 15, but I know I had trouble with 11 because there was an 8.
Okay, 11. Will Maynes burns a 0.6 gram peanut beneath 50 grams of water, which increases in temperature from 20 degrees Celsius to 50 degrees Celsius. The specific heat of capacity of water is 1 calorie per gram degree Celsius. Assuming 40% efficiency, show that the peanut's food value is 3,500. Okay, so this is a long, drawn-out problem.
Yeah.
And it has one piece that's in today's lecture. So I don't think I can copy and paste very effectively here.
Which one are we doing?
Number 11.
Which is what, 36?
Yes.
Who?
Oh, so I had a question. Was it 36 or 49? Because in the book, wait, what homework is this?
The one that's due today.
So I think I did the wrong homework.
Uh-oh.
Oh no. Well, okay, like I'm low-key at. Isn't it this? Just let him do this thing. Why do you? Because it makes my heart feel better. Oh, okay. I did do it. Thank goodness. I started on next week's homework. Okay?
Why?
Because
she's
I like to
hardcore
read
that
it.
way.
And it takes forever to listen to these lectures. It takes 15 minutes every time.
All right, so here's the problem. It doesn't have the A and B. We got all the numbers. So what we have is, here's the peanut. We burn it, so what happens is the heat comes off. Q is actually the symbol for heat. I don't think I told you that yet. Q is equal to the heat. And that's what we're actually trying to find, is the heat. Because how many calories? Well, actually, no. Show the peanut's food value is 3,500 calories. So we're going to find the heat and show that it's 3,500 calories. So we start with Q as heat. That heat is then going to go, so 40% of heat goes into water. So in other words, Q times 0.4 goes into water. And now comes a new thing, something that's in today's lecture. So we'll have it right here, and I won't have to lecture again. When you heat up things, two things can happen. Thing number one is when you heat it up, the temperature can get hotter. And that's what most people think is always what happens when you heat something up. But it's not always what happens. If you heat up ice, what happens to the ice? It melts. You still heated it up. You put heat into it. But that heat went into breaking bonds rather than to raising the temperature. Because remember, temperature is a measurement that's proportional to the average kinetic energy, but it's different for different phases of material. So when you have a solid, the molecules are basically fixed in place and just jiggle. And so they have the energy in that vibration. And if they vibrate hard enough, they'll break free. And so when you melt something, you're putting in energy to make it break free instead of move faster. So the temperature changes zero while you're changing phase. If you're not changing phase, then when you heat it up, it gets hotter. So we have a relationship. The heat you put in is equal to, what does M stand for? Mass. What does delta T stand for? Okay, temperature, because it's capital T. Lowercase t would have been changing time. Capital T is changing temperature. The C is what we call the specific heat capacity. And that's something that's different for every material. And so with water, we're given in the problem that the specific heat capacity of water is 1 calorie per gram degree Celsius. So for water, we have C is equal to 1 calorie per gram degree Celsius. So now I can put my values into this. I am writing really big, it turns out. Well, c'est la vie. It's just big writing. So what I'm going to do then is say that Q times 0.4 is equal to the mass. So I look at this and it tells me the mass of water was 50 grams times C, which is 1 calorie per gram degree Celsius, multiplied by the change in temperature. So it went from 22 to 50. So the change in temperature is going to be 50 degrees Celsius minus 22 degrees Celsius. And I can use this then to find Q. So I have 50 divided by, 50 minus 22, by the way, is what? 28? 50 times 28 divided by 0.4. Y over 0.4 because I wanted to get Q by itself. So 50 times 28. 28 is 7 times 4. And so 28 divided by 0.4 is 70. And so 70 times 50 is 3,500 calories. Notice my units, grams cancel with grams. Degrees Celsius, cancel with degrees Celsius. That was fun. That's only part A. Part B. Okay, I got to read the problem again. Then show, wait. Show the peanut's food value is 3,500 calories. Then show the food value in calories per gram. Okay, so then we just take that in calories per gram. So Q over M for the peanut is equal to 3,500 calories divided by, and it was 0.6 grams, right? Yeah. So 3,500 divided by 0.6 is 5, 8, 3 repeating. So 5,833 and a third calories per gram. Notice the units up here aren't calories per gram. They're kilocalories per gram or dietary calories per gram, because a dietary calorie is a kilocalorie.
So then you have.
So 1 kilocalorie is equal to 1,000 calories. So I just take that number and divide by 1,000 to get it into kilocalories per gram.
Oh.
So, go ahead.
When we write the homework, do you want us to write it like 1 kilocalorie per thousand, like show?
You need to have something to show going from 5,833.
So if we just divided that 5,000 by 1,000, that would.
That's exactly what I have in this right here.
And what I'm saying, if we don't have like the one part, is that so?
I probably won't mark you wrong. You should have it because you're changing the units. All right. Do you understand, Grace?
I think so.
I know you could have it written down, but understanding is much more important to me than having it written down.
It's a lot of stuff. But yeah, I think. Wait, so with the first part though, we just had to find for the specific heat, we used the specific heat of the water, not the peanut.
Because we were heating up the water, we used the specific heat of water.
Right. I thought we were heating the peanut too.
In the beginning part here, we're burning the peanut. So we're releasing the energy from the peanut. Combustion is releasing the energy, basically. And so we're releasing that energy, and then 40% of that energy is going into the peanut as heat. So that's where we started. We said the heat is 40% of the energy that's released. 40% of the heat that's released from the peanut is going into heating water. And so that first calculation, 40% of Q equals MC delta T, is saying the heat going into the water is equal to MC delta T, mass of the water, C of the water, change the temperature of the water. Okay, now was there another homework question?
Yeah, I think I had trouble with 12, and that was it, unless I think it was 12. But
okay, so number 12. Suppose that the 1.3 kilometer main span of steel for the Golden Gate Bridge had no expansion joints. Show that for an increase in temperature of 20 degrees Celsius, the bridge would be nearly 0.3 meters longer. Now, in class yesterday, I gave a demonstration. We talked about when you heat things up, they expand. And so for this here, copy that. Go back to here, create a new page. Page manipulation, insert. Okay, so for this here, there's another equation that goes with that expansion. And that equation is actually a real simple equation, but you have to look up a number. Oops, I'm on the non-drawing tool. What was that?
I don't want to say it wrong.
Okay. Change in length is equal to the original length. So L sub 0 is the original length. Delta L is the change in length. Yeah. And then we have something that is alpha delta temperature. So once again, everything there makes perfect sense except for the alpha. Alpha is called the coefficient of linear expansion. And just like the specific heat, it's different for every type of material. So you need to look up. Anybody have their textbook with them? Because I can't do this without looking it up. I don't have it memorized either. You have to look up what alpha for steel is. Siri. I'm using this instead of my phone because I trust it more. What is the coefficient of linear?
I couldn't find any matching places.
What is the coefficient of thermal expansion for steel?
Okay, I found this on the web for what is the coefficient of thermal expansion for steel.
Yeah, well, I'll go to a website then. And according to the website Siri found, it's 13 times 10 to the minus 6.
I was right.
Per degree Celsius. No unit on top, just unit on bottom. So you did this problem, I assume.
Oh, yeah.
And so we just put our numbers in. So that's going to be the original length. I'll put it in meters. 1,300 meters is 1.3 kilometers. Times that alpha, 13 times 10 to the minus 6 per degree Celsius. And increase in temperature says for an increase in temperature of 20 degrees Celsius. And so if you look at the units, you'll see the degrees Celsius cancel. I'm left with meters. And so I have 1,000. I am not going to trust Siri to do that. I will end up spending 5 hours just trying to get her to understand my words. Sometimes I feel like, I can't remember his name, something Wolowitz.
I know you don't know.
Siri doesn't, yeah, he goes on a rant about how Siri is crap and just can't understand speech because, of course.
You just think you're
What?
Nothing.
Okay. So that gives us 0.338 meters. So how much longer would the bridge be? To one decimal place, 0.3 meters longer. Does that matter? Well, how much is 0.3 meters? 0.3 meters is this much distance. If it's just about a foot. If the bridge expands by about a foot and you don't have expansion joints, it's going to buckle. That's not good. That happens periodically in places when you have a really cold or really hot temperature. Things will expand more than it's designed for. You know, when you drive on the freeway and you have those annoying thump, sounds like you have a flat tire.
Yeah.
Those are expansion joints built into the freeway, so the freeway won't buckle on a hot day. Because on a hot day, the length between Lincoln and Omaha is staying the same, but the length of the freeway is getting longer. And so you have to have those expansion joints so it closes them up, and you won't have big gaps on a hot day, but you'll have big gaps on a cold day.
So is that the answer?
That is the answer, yeah.
What did you?
No, it's the show. You're already given the number in the answer. A lot of these, you can look at the back, it doesn't help you because it gives you the answer, and then question.
I totally got a different answer, because I think I did it wrong.
It would be in the multiplication.
What did you multiply 20 by?
I multiplied 1,300 by 13 times 10 to the minus 6 by 20.
See, the equation I
All three
had
multiplied
was
together.
1,300 times 11 times 10 to the negative 6.
Times 11?
Yeah.
We have to use a stick figure
Okay,
out.
then that's it was 13 rather than 11.
Because I looked in the book for the, I'm so confused.
It could be different, but it is a standard number. It shouldn't be.
I know, I didn't do that. I'm confused because I don't know if the book had a different equation than.
When class is over, let me look at it real quick, okay?
Well,
Look
it's
at your
turned
work.
in, so you can just look
Oh.
at it then.
Okay. Well, you might want to adjust it and turn it in again.
I'll look at it again tonight.
Okay. Turn it in. Look at her being so ahead of the game.
She had it done on Sunday.
Way ahead of the
I
game.
always do it on Sunday. If I don't have time.
Okay. Let's see. Yes. So getting into the lecture.
Yeah, that we only have 20 minutes.
Yeah, indeed. So this is something we actually talked about last class period. We talked about heat is measurement of energy transfer, and then we have heat flows from higher temperature to colder temperature. So in this case where I have the hot water and the cold water, the hot water has more energy per molecule. But if I bring the two together, heat is going to flow from the hot water to the cold water, even though there's a lot more water in the cold water, hence more total energy in the cold water. Because we have a lot more water here, if we heat it up, the heat has to go into a lot more material. And so the amount of heat per molecule is going to be less, hence the temperature rise is going to be less. So little water will heat up quicker than a lot of water. And you probably have noticed that when you're cooking, right? If you have a big pot of water, it takes forever to boil. If you have a small pot of water, it just takes a long time. Because less water, you put in the same amount of heat, it is going to raise temperature quicker. And that's because of this relationship we looked at right here. The heat equals MC delta T. So if you put heat in at a constant rate, that is, if Q per time is constant, then the change in temperature per time is going to be dependent on M and C. Now, there's some important things about life in general here, right? In this class, I think I said last class period before, there's a lot of material coming at you. It's kind of hard to, can I memorize everything? No, you can't really. But learning important things, like when you put heat into something, it either changes phase or gets hotter. That's important. And here's another really important one. Water, we already did that problem, so we don't need to talk about that. We've already talked about that too. Water, oh goodness. I want to get to the one that has water. Okay. Water is an important thing on Earth. We have a lot of water on Earth. And water, compared to most materials, has a high specific heat. That means it takes a lot of heat flowing in or out to change the temperature compared to most things. For instance, if I have aluminum, if I have equal masses of aluminum and water, and I put the same amount of heat into them, the aluminum's temperature will go up more than 4 times the amount that the water's temperature goes up. Right? It doesn't take that much heat to make aluminum hot. It takes a lot of heat to make water hot. It's a difference in the structure of the materials. Because of that, water is kind of a thermal buffer. That is, water will keep the temperature from fluctuating a lot. So if you live near the coast, and as you probably know, I grew up in Monterey Bay County, right there on the coast, you have all of that water. During the daytime, the sun is heating up the water, right? But because there's so much water, the change in temperature of the water is virtually nothing. And then at night, the air gets cold and the water heats up the air above it. But once again, the heat going out hardly changes the temperature of the ocean water at all. So that means the air around the ocean is going to remain reasonably constant in temperature. So I grew up right on the coast, right? Monterey Bay Academy is beachfront property. And so our temperature, the hottest it ever got was about 80. And the coldest it ever got was about, well, it got down to maybe 30 every now and then. Very small fluctuation in temperature. Now you come here to Nebraska. Where's the nearest large body of water here?
I'm just kidding. I'm just kidding.
It is.
It's pretty much still California, right? We don't have any large bodies of water anywhere close to us. So that means that during the hot day, the sun is beating down, instead of beating down water, it's beating down things like rock, which heat up much more rapidly. And as a result, the air will heat up much more rapidly. And then at night, it can cool down more. So the temperatures can vary much more. You go to a desert where there's no water, it'll be 120 during the day and 30 at night. Yes. Because that rock doesn't have a very high heat capacity or specific heat. And so the temperatures can vary quite a bit. So that's a really important thing for us to understand. That's why, now there's other things like the direction, we have a thing called the Coriolis effect. Winds tend to come down and blow east. And so in California, we tend to have breezes that are coming from the Arctic, going over the water, being warmed by the water, and then coming to land. If you're on the eastern seaboard, you have air that comes down over the continental mass and then comes to the coast. And so they get cooled by Arctic air that came over the Earth. Or they can get heated up by air that comes up from the equator over the Earth. So the temperature variation is much bigger on the eastern than the western because on the west coast, we have the water coming over or air coming over the ocean to come to us. And I told you, our temperature didn't vary much. Well, when we went shopping in Watsonville, it's only like 8 to 10 miles away. Temperatures would be much warmer in the summertime there because they weren't right on the ocean. They weren't close to that temperature buffer of water. So being near water makes a big difference. And well, I have to mention it. You guys heard about the lake effect? It's really significant.
Yeah, that is fun.
You do?
Yeah.
Yeah, Great Lakes breed lake effects. If you live somewhere like, in the area of Niagara Falls, I think, or Erie, Pennsylvania, you have places where they get enormous amounts of snow. Like, hey, this snowstorm brought us 5 feet of snow. Yeah. You're like, how in the world does that happen? Well, it happens because you have a lake, and so the lake's going to put a lot of moisture in the air, and it's going to modify the temperature. And so you put a moisture, and then you get the temperature right, and it just dumps it all at the end of the lake. And so you have huge amounts of snow that occur because of the water blowing over the lake.
Oh no, that's
There was one more thing I was going to say, but
So the lake effect is when huge amounts of snow form because of the water that's in there.
it's fairly complicated, but it has to do with the waters buffering the temperature as well as putting a lot of moisture into the air. One more thing about water that is very important in practical real-life scenarios. One of the things we like to do is to live. And water is really important to life. And you might think, okay, yeah, water is important to life because our bodies are, 70, whatever percent water. But it's more than just that. Things like, we have Holmes Lake over here, or Holmes Pond. I called it a pond when I first arrived, and I was shy that around these parts, the body of water that size is called a lake. When it gets cold, people like to go out there and ice fish. Why? I don't know. I mean, it's not like we're in Minnesota, but they do. And they can walk on the lake. Why is it possible to walk on the lake? You all know the answer. Why is it possible to walk on the lake? It's frozen. How much of the lake is frozen?
The outer edges.
Just the top part. And actually, right next to the ground is where it's the weakest.
Oh, really?
Because the earth tends to be a little warmer, and it'll make it so you don't have as much ice there. So it's only frozen on top. Why only on top, you ask? Well, the first part of that is real simple. Where's the cold air touching the water? At the top. So heat goes from the warmer water into the colder air. Temperature in the water drops until you reach freezing temperature and the water on the top freezes.
Okay, if that's true, why is it when you get deeper and like a lake or whatever, it's cooler when you're in I'm just saying.
I don't have experience or knowledge about that, so I can't actually answer.
I'm just saying, like, if you go swimming in a lake in the dead of like July when it's really hot,
Oh,
you get
in the middle of the
and-
summer, yes, I can answer that.
and like your upper half is warm. That is not true.
That wasn't advice.
I'm just saying.
Okay, in this case, that actually is an easy to explain phenomenon. In the middle of the summer, you have solar radiation. The solar radiation is largely being absorbed in the upper portion of the water. And so you also have air, of course, is exchanging heat with it. So the surface of the water is going to be much closer to air temperature and being heated by the sun. You go down further and you don't have that proximity. And it takes time for heat to conduct through the water, right? It's not a great conductor of heat. And so that's why the surface is hotter. The same thing occurs in sand in a much greater effect because sand is pretty opaque. So like when I went to the beach in college, I got the skin grafts on my feet from burning my feet walking through coals, spat gland. I was 13 months at the time, so it wasn't a stupid idea. It was a kid didn't know better. But my feet are really sensitive because I have skin grafts on them. And so I walk on the sand and my feet are just burning. But I learned quickly to just twist my foot, get it down below the top, and then it's fine. Because the sun's energy is being absorbed by that top layer, which gets really hot. It's not reaching anything lower, so that's not being heated up. And rock is a really poor, especially sand where you got a lot of air gaps, conductor of heat, so it's not hot underneath. It's fundamentally the same ideas. Just a lot easier to visualize with the sand.
Yeah.
Okay, so back to the importance of life. I'm never going to finish this lecture. The importance of life that I'm talking about. Ice-free, the water on the lake is going to freeze to the top. But then what happens when it freezes? It turns into solid. It floats. Ice is bizarre because it's less dense than water. And like I said, when we get to the chemistry part, we'll actually learn about the why of that. But because ice floats, then you start forming a layer of ice at the top of the lake. If ice didn't float, it would sink to the bottom. And then we'd freeze more water on top and it would sink to the bottom. And lakes would freeze from the bottom up. And we would freeze our lakes solid in many cases. And so now there are some fish you can just freeze and basically hibernate. But what that would do would actually make the earth too cold for us to live here. But because the ice floats, we form a layer of ice on the top that acts as an insulator to keep heat from going from lower in the water up out to the air. And thus, we can have fish swimming around into their happy as pie in water that's, a good 35 degrees Fahrenheit when it's minus 20 degrees Fahrenheit outside. And so that's another thing that's really important for life on Earth is that God created water so it would have a special property that would make the frozen state float on the liquid state. Okay, so we totally have 6 minutes left. I'm not going to go back to the slides. I skipped over. Well, I will. There are some important things here. I skipped a lot of stuff. The laws of thermodynamics are important. So, the laws of thermodynamics. There are 4 laws of thermodynamics. The laws are very conveniently named the first law, the second law, the third law, and then they realized there was something really, really fundamental that they had skipped. And so they said, well, we already got 1, 2, and 3, and this one's more fundamental than 1. And so there's the 0th law. So here are the laws of thermodynamics. The 0th law, if temperature A equals temperature B and temperature B equals temperature C, then temperature A equals temperature C. That seems pretty obvious, right? If A equals 5 and B equals 5, then A equals B, basically. But that's why it wasn't named initially. It seemed really obvious. But when physicists got a better understanding of what temperature is really measuring, they realized, ooh, it turns out that wasn't obvious. It seemed obvious, but it wasn't. The first law, I've run out of space on the left, so I'll put the first law on the right. The first law of thermodynamics says that energy cannot be created or destroyed. So energy must be conserved. Conserved, don't ask this, it's already a question that's been asked for potential test questions. Conserved means you can't create or destroy it. Now, we've already talked about things like that. We have elastic collisions. In an elastic collision, kinetic energy was conserved. Energy is always conserved. In an elastic collision, kinetic energy was conserved. We can move energy from one thing to another via work, or now we have heat. Two ways of transferring energy from one way to another. But you can't create it or destroy it. You can only transfer it. So when we had that peanut, it had energy that was chemical energy. We burned it and we released that chemical energy, converted it into heat, and then that heat we converted into another kind, and the energy can move around, but you cannot create or destroy it. And that makes somebody say, well, how can we possibly have an energy crisis if you can't create or destroy energy? It's just a constant. Any answers to that?
We don't burn peanuts for energy.
We don't, but we could. Grace?
Because it can be in different forms, and it might not be in the form we need.
Okay.
The way we need to
Energy can be in different forms. It may not be in the form we need. We have limited resources that we can easily transfer into energy we use. So we use energy that comes from, let's say, burning gas, burning oil, or burning peanuts. There is a limited supply of oil in this world. And so when we talk about an energy crisis, we're usually talking about oil. We're not able to pump the oil out of the earth fast enough for how quickly we're using it is what the energy crisis starts out as. And then the more futuristic thinking people say, yeah, and if we keep doing this, we're going to run out of oil. And then we'll really have a crisis. There still would be energy available, but not in that form. So we burn oil, we release it, put it in another form. There are other methods of energy conversion that are not a problem. They're renewable, like peanuts. We can grow goobers. We can grow them year-round probably in some parts of the world. And then you can burn them. We call that biomass fuel. And it's very renewable. You can just keep going and keep going, making more peanuts. Or what do we actually use? Yes. In this country, we use corn rather than peanuts. But we grow corn, and then we process that to extract ethanol. Well, to extract and ferment, I'm sure, ethanol. And then we burn that ethanol in our vehicles. And that's a completely renewable resource because we can just grow more corn. Where's the energy ultimately coming from as we're growing this corn? The sun. The sun is the ultimate source of energy here. Okay, so the second law, we've actually talked about the second law. It says, heat flows from hot to cold. Now, there are a couple very different statements of the second law, but that's the one I like the most. Heat naturally flows from hot things to cold things. We've already talked about all of the things here so far. Well, we didn't talk about the 0th law, but we talked about conservation of energy. We talked about heat flowing from hot things to cold things. That's just the second law of thermodynamics. And then the third law says that nothing can reach absolute zero. Right.
Otherwise, it would just.
There is a very easy Gedonken explanation for that, the thought explanation. Basically, to cool something down, you have to have something colder, so heat will flow out of the hotter thing. But to reach absolute zero, then you have to have something colder than absolute zero, so heat can flow out of it to reach absolute zero. All right, apparently it's time for break. Have a great long weekend. I'll see you next Monday. No, we won't have a quiz on Monday.
Is our exam next Friday?
You'd have to look at the syllabus.